Today's 4.5a. And we've been talking about area in chapter 5, but now we're back to chapter 4, so we're going to talk about slope. And we've dealt with slope of a curve at a point a lot. So there's the tangent line that represents how steep the curve is. So up until now, we have used the tangent line slope to give us the exact slope of a curve at a point. Now we've used the tangent line slope to give us the exact slope of a curve at a point. So we just graphed this point here, or graphed this line here, to represent how steep the curve was. And the steepness of this line is the exact steepness of that curve. Okay, so today we're going to use the tangent line for a little bit of a different approach, though. Instead of using the tangent line as the slope of the curve, we're going to use the tangent line as the heights of the curve. So today, instead, we will use the tangent line to approximate the height of the curve. So the reason we can do that is, at this point right here, at this x value, the height of the line is sort of and pretty close to the height of the curve. So since the height of the line is pretty close to the height of the curve, we're going to use that height to approximate how the y value for the curve. Okay. And in this context, the tangent line is called the linearization of the curve. In this context, the tangent line is called the linearization of the curve. Yeah?
Would that only work for like that small region that is close to the curve?
Yeah, that's a good point. Out here, it starts getting pretty to be a pretty bad approximation. Yeah. So this is going to be what we base everything off of. This number here is going to be a certain x. We're going to call that a. And then, yes, we'll know that in our minds that you have to be close to a in order for the approximation to be good. Yes. But it's a different way of looking at the tangent line. We're still going to find the equation of the tangent line. Now, instead of using it for the slope of the curve, we're going to be using it for the heights of the curve. And so that's why there's a new name for it, the linearization. But it's not anything new. It's still the tangent line. So it's just got a new vocabulary word with it. So in example 1, f of x is the cube root of x. And for part A, find the linearization of f at a equals negative 8. So it says find the linearization. And we just learned what the term linearization means. It means the tangent line. So when it says find the linearization, another way to say it is just find the equation of the tangent line. And we've been doing that for a long time, so it shouldn't be too bad. So we want to write the equation of the tangent line. So that means our final product is going to be y equals mx plus b. And to figure out the slope of the tangent line, you just take the derivative. So another way to write the cube root of x is x to the 1/3 power. So you just take the derivative of that. Derivative of that is 1/3 x to the negative 2/3. And then you just plug negative 8 into that to get the slope at negative 8. So derivative at negative 8 is 1/3 times negative 8 to the negative 2/3. The 3 on the bottom there means cube root. So we're going to take the cube root of negative 8, that's negative 2. And then the 2 means square that. Negative 2 squared is 4. And then the negative means flip, so that's 1/4. So this is 1/3 times 1/4. So the derivative is 1/12. So that's the slope of the tangent line. So you just plug that in for m. Got y equals 1/12x plus b. And we know what the x value is. The x value is negative 2. Or sorry, negative 8. And to get the y value, we just plug it in here. The cube root of negative 8 is negative 2. So there's our point that the line goes through. And we just plug that in to get our y-intercept. So x is negative 8. Y is negative 2. So that's negative 2/3. And negative 2/3. Negative 2 plus 2/3 is 1 1/3. So 4/3. Negative, sorry. So the tangent line is 1/12 x minus 4/3. And so the linearization, sometimes we call it L of x for linearization, is 1/12 x minus 4/3. So this is just y equals 1/12 x minus 4/3. But since it's called the linearization, sometimes we use the capital L of x to stand for the linearization. Okay, so for part B, we're going to use the linearization to approximate f of negative 7.9. Okay, so we could plug negative 7.9 into the original f and get the exact answer, but it asks us instead to plug negative 7.9 into f to approximate. So into the L of x. So we're going to plug negative 7.9 into this. So that's L of negative 7.9 is 1/12 times negative 7.9 minus 4/3. So I think I have that answer over here. It's negative 1.9916, and the 6 is repeating. And then for part C, we're going to ask how accurate is this approximation. Hey, how's it going? Good. Good to see you, man. Things going well?
Yeah, glad you're back.
Just so you know, you're on tape.
Awesome.
So you can't break out any cuss words. I know you were going
Oh,
to.
no, I was
Yeah. I can't believe last year. No.
I wanted to stop in and say that I told everyone that 0.9 repeating is the same numerical value as 1. And
Yeah,
they
these
believed
guys,
me.
I told them this
Yep,
year.
That's
and
the only thing we'll remember. That's the only thing I remember. Really. I didn't know how to do my taxes.
Well, it's good
Yeah.
to see you.
I wanted to stop and say hi.
Yeah, I'm glad things are going well.
Mhm.
Yeah, take care of yourself.
You too.
Yeah. Yeah, my discrete math class last year, I told him 0.9 repeating was equal to 1. And that he was really the only guy who believed me. And so he tried to convince his recruiter that that was true. And his recruiter wouldn't believe him. So he'd come in every day and he's like, what's another way I could try to convince him? And so I'd give him another, and he'd go back. I don't think his recruiter ever believed him, but anyway. He's going to know that forever. Anyway. Okay, so the question is here, how accurate is the approximation? Hey. He's not here right today, I guess. Yeah. I wonder if anybody else is going to stop by. Maybe Donald Trump, I don't know. How's it going? All right, so the question is how accurate is the approximation? So here's our approximation that we got, negative 1.9916. And now I'm going to plug negative 7.9 into the actual function to see what the right answer is. So I'll take the cube root of negative 7.9. And I did that another year, and it's negative 1.9916 31701. So to get the error, I could take the correct answer and the approximation and subtract them to see how far off it is. So it's negative 1.9916 repeating minus negative 1.9916311701. And that error is about 0.00003. Okay, so the idea is that the cube root curve looks like this. And it goes through the point -8, -2. And we decided to find the equation of the tangent line at that point. So So that was this, right? And since we were using the tangent line to approximate the curve, we called it the linearization. So this tangent line here is called L of x, the linearization. And what we did was we plugged negative 7.9 into the curve. Let me exaggerate. Let's say it's over here. We plugged negative 7.9 into the line, and we got an answer. And then we plugged negative 7.9 into the curve, and we got a different answer. But they were only off by a very little bit. So the linearization is a good approximation, a good way of getting an approximation for the height of the curve. And you can see here it's off by a fair amount, but at 7.9 it would be off by very little, and we even found out that the amount that it was off by was the 0.00003. Okay, so nothing big and super hard today that's new. We're just using the line to approximate the curve rather than the line to find the slope of the curve, but it's still the same line, it's still the tangent line. All right, for example 2, we're going to use a linear approximation. To estimate 1.97 to the 6th power. Okay, so this one is a little bit more vague because it doesn't tell you what the function is and it doesn't tell you what the a is. So in the last problem, we had f of x equals the cube root of x, and then they told us a was negative 8. Here we're just supposed to come up with what f of x is and what a are based on this information. So it's a little bit tougher, but it's still the same concept. Okay, so what do you think the function should be? What's happening to the 1.97? Yeah. It's being taken to the 6th power, right? So since we're going to take something to the 6th power, that's what the function should be. F of x should be x to the 6th. Okay, now we need to decide what number we should base everything off of. And as Lauren pointed out earlier, the number you base things off of, like here we were based on negative 8. A was negative 8. As you get farther away from negative 8, the approximation gets worse, right? So you don't want to pick something really far away from where you're trying to approximate, because then your approximation is going to be far off. So we need a number close to 1.97. That's going to give us a good approximation for 1.97. But we also want it to be easy to work with, right? So 1.98 is close to 1.97, but 1.98 to the 6th isn't any easier to do than 1.97 to the 6th. So we want to be close, but also pick a number that's reasonable to work with. So obviously on this one, a should be 2. So a is 2 because it's close to 1.97, so it's going to give us a good approximation, and it's easy to work with. We can do 2 to the 6th in our head. All right, so now that we picked our function and our center, you see I slipped that word in there, right? The center. Everybody in VC with me? The center. Okay. All right, so since we picked f of x of that, and it's nothing you guys need to know, I'm just jogging their memory, sorry. So here's our function. Now we're going to write the equation of the tangent line. So let's see, I need the slope of the tangent line if I'm going to find the equation of the tangent line. So that's 6x to the fifth. So then you just plug 2 into that. So 2 to the fifth, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, so 2 to the fifth is 32. I'll multiply that by 6. That comes out to 192. That means the slope is 192. So that means when we write the equation of our line, it's going to be 192x plus b. Just putting the 192 in for m. And then I'm going to plug 2 into the function to get the point that I'm based off of. 2 to the sixth is 64. So now I just plug 264 over here to get my y-intercept. So 64 equals 192 times 2 plus b. 64 equals 384 plus b. So b is negative 320. Y is 192x minus 320. So this is just the equation of the tangent line at the point 2 comma 64. But today, we're calling it the linearization. So we'll label it as L of x, just for linearization. Okay, the whole purpose of the problem was to approximate 1.97 to the sixth power. So I'm going to plug 1.97 into the tangent line equation, and that's going to give me a good approximation for what 1.97 to the sixth is. So that's 192. That should be a 7, sorry. Times 1.97 minus 320. And that comes out to 58.24. So that means that 1.97 to the sixth power is pretty close to 58.24. Because we plugged it into the tangent line and got that number. And the tangent line is the approximation of what the curve would actually be, the height of the curve would actually be. Okay, just one more problem. Example 3 is use a linear approximation to estimate the sine of 59 degrees. So what should f of x be? Sine of x, good. And then a should be a number close to 59 that we know how to take the sine of. So that's 60. Because 60 appears on the unit circle. So we can do the sine of 60 theoretically with the unit circle. Okay, so we're gonna, so f of x is the function that is happening in the problem, and then a is something close to what you're trying to approximate that you can work with easily. So we're gonna write the equation of the tangent line. So we'll take the derivative to get the slope of the tangent line. Derivative of sine is cosine. Then we'll plug 60 into that. So that's the cosine of 60. So we'll look at the unit circle. And 60 degrees, which is pi over 3 radians, is up here. And the point is 1/2, comma, root 3 over 2. So the cosine is 1/2. So the slope is 1/2. That's y equals 1/2 x plus b. So really, since I'm in calculus, well, since I took the derivative of sine and got cosine, when I did that, I decided that I was in radians instead of degrees. So really, I should be having my a be pi over 3. So a is pi over 3. And so I have to find my y value that goes with that. So pi over 3, comma, whatever it is. So to figure out the y value, I have to plug the pi over 3 into the original. So I have to take the sine of pi over 3. But that's the y value on the unit circle. So that's root 3 over 2. So now I have my point that I can work with to find my y-intercept. So 1/2 times pi over 3 plus b should spit out root 3 over 2. So that'll multiply out to pi over 6. I can subtract the pi over 6 to the other side. So b is root 3 over 2 minus pi over 6. So my linearization is 1/2 x plus that y-intercept. And now I'm just going to plug what I'm trying to approximate into that, which is 59. But the problem is I'm not allowed to plug 59 degrees into that. I have to convert it to radians first. So the conversion formula is r over pi equals degrees over 180. So you cross multiply that. 180r equals 59 pi. So r is 59 pi over 180. Wonder if I got a decimal for that. No, not until the very end. So this mess here is just 59 degrees in radians instead. So now I just plug that into here for my x. So 1/2 times 59 pi over 180 plus √3 over 2 minus pi over 6 comes out to 0.857 298 7575. So that means that the sine of 59 is about that number. Okay, so today's lesson is not anything brand new, but it's looking at it from a different angle. So we used to use the tangent line to find the slope of the curve. And now today we're just using the tangent line to approximate the heights of the curve. But still a tangent line, just a different way of using it. Over the weekend, I thought about getting a brain transplant, but then I changed my mind. So did I get a transplant or not? I don't know. That's why it's funny.